In the previous section, we presented the fundamental theorem of calculus, which in one hand gives us a method for um, evaluating the definite integral, provided we have an antiderivative. But also the first part of that theorem says that every continuous function has an antiderivative, namely the integral from a to x of f of t dt. This will always be an antiderivative. So in this section, we're going to investigate antiderivatives, kind of characterize them, as well as develop some methods for evaluating them. So first off, let's get a handle. If f of x is any antiderivative, then I can add a constant to it, and this will also be an antiderivative, right? Because if f prime of x is little f, then since the derivative of a constant is 0, then take the derivative of this function, it's just little f plus 0. More importantly, though, is this theorem that states if I've got any two antiderivatives, then their difference is a constant. In other words, if I have two antiderivatives, say big G of x and big f of x, then they're equal to each other plus a constant. So once I have one antiderivative, then I have the entire family of antiderivatives. And we're going to give ourselves a definition of this family. So let's suppose that f has an antiderivative. Then the family of antiderivatives is called the indefinite integral. And we denote it like this, with the integral symbol without any bounds of integration. So if we've dropped the bounds of integration, then what we're asking for is the entire family of antiderivatives, namely some particular antiderivative plus a constant. And finding antiderivatives, one, is important for evaluating the definite integral, but also we'll find it's very applicable when, say, we have the velocity of an object, then if we anti-differentiate, we get its position. Or if we have the acceleration of an object, if we anti-differentiate, the indefinite integral will be its velocity, and so on and so forth. So this next theorem just states some rules that should feel pretty straightforward. First off, if the antiderivative of the differential of u is simply u plus a constant. Constants can be factored out of the antiderivative. Why should that be? Well, constants can move in and out of the derivative, right? This, kind of think of the antiderivative as the inverse of the derivative. So since dcu is equal to c du, right? The constants can factor through the differential, or the differential just moves past constants. The same thing is true for antiderivatives. Similarly, since the differential of u plus or minus v is the differential of u plus or minus the differential of v, then it should make perfect sense that the same is true for antiderivatives. The power rule comes from our power rule of differentials, right? Because du to the r is equal to r u to the r minus 1 du. And so if I've got a power rule, then for differentiating, we subtract and it comes down as the coefficient. But now, if we're anti-differentiating going backwards, then the exponent increases by 1, and then we've got to divide by that in order to have a coefficient of 1. The antiderivative sign is negative cosine, since the derivative of negative cosine is sine. The antiderivative of cosine is sine, since the derivative of sine is cosine. The antiderivative of e to the u is e to the u, since the derivative of e to the u. And then the one that is maybe feels a little bit weird here is that the antiderivative of 1 over u is equal to the natural log of u. But again, if you remember our natural log functions, differential of ln of u is simply 1 over u du. So going backwards, right, we get that, oh, well, 1 over du is the same as the differential of ln of u, and then coming back to rule 1, we get that the antiderivative of 1 over u would be ln of u. We put in the absolute values. Why should that be? Well, we don't know the value of u. It could be negative, it could be positive. Natural log is not defined for negative values, so we have to put the absolute values there. So, without further ado, let's work some problems. So let's compute the antiderivative of 5 plus y to the negative 2, I don't know, minus 4y to the minus 3 dy. So since I don't have any bounds of integration, I am looking for the indefinite integral. I'm looking for the antiderivative of this function. So I can break this up if I wish. So this is 5 dy plus antiderivative of y to the minus 2 dy minus 4 antiderivative of y to the negative 3 dy. And now the antiderivative of a constant is just 5. So this would be 5y. The antiderivative of y to the negative 2, so I have to add 1. So if I add 1 to negative 2, I get a negative 1. And then I divide by 1 over negative 1. Then I have minus 4 times, and again, I add 1, so it'll be y to the negative 2. And then I divide by that exact same number. And then everybody gets a constant, so I just write it as one single constant. Simplifying this would be 5y minus maybe 1 over y. These two cancel, so it'd be plus 2, 1 over y squared plus a constant. And that's the indefinite integral of this function here. So let's just practice with another one. Let's say the antiderivative of y to the 2/3 plus 7, say y to the 4/5 dy. And as long, in this power rule, as long as r is not negative 1, so that's our number one kind of rule here, our power cannot be negative 1. If the power is negative 1, then we're in position rule 8. But as long as the coefficient here is not 1, then our rule just says add 1 and divide by its reciprocal. And doesn't have to be an integer. It can be a rational expression like this. So again, I'll break it up. So this is equal to the antiderivative of y to the 2/3 dy. And I'll factor the 7 out, antiderivative of y to the 4/5 with respect to y. Now so this is equal to 2/3 plus 1, so that's 2/3 plus 3/3, making this a y to the 5/3, and then I have to multiply by its reciprocal, which is 3/5. Plus 7 times y. Okay, now it's 4/5, so I add 1 to it, or I add 5/5 to it. So the new exponent is 9/5, and the coefficient will be 5/9. Then it's plus a constant. Simplifying just one more step, so it's 3/5 y to the 5/3 plus 35 over 9, y to the 9/5 plus a constant. So that's two examples of using the power rule, pretty straightforward. How about this one? The antiderivative of x minus 2 times, say, 2x plus 1. Now, something that I will see students do often is try to think of this as some kind of like distributes across multiplication. So I'll declare this quite vehemently that this is wrong. I'm going to do it anyways just because I see it, but notice what I'm doing is not true. So this is the wrong approach, but sometimes it's educational to see things done wrong. So to think that, oh, well, it distributes across addition, maybe it distributes across multiplication as well. So maybe this is equal to the antiderivative of x minus 2 dx times the antiderivative of 2x plus 1. Right? So what would that be? So the antiderivative, I'm not going to go through all the steps of breaking this up against addition and subtraction. We know that the exponent here will go up by 1, so it'll be x squared, but then I need to multiply by its reciprocal, so 1/2. The antiderivative of 2 is 2x plus some constant, and then I'll multiply this by this antiderivative. So that'll be 2x squared, and then I divide by or multiply by its reciprocal, plus x plus maybe some other constant. Right? And I want to point out that this function is not an antiderivative of this function. Why not? So let's call this, g of x. If it is an antiderivative, then when I take its derivative, I should get this function. But g prime is, okay, I've got a product, so I've got a product rule. So it's the derivative of this. So this is just going to be x minus 2. That's the derivative of this guy times this thing, which is x squared plus x plus d plus 1/2 x squared minus 2x plus c times the derivative of this, which is 2x plus 1. And note that this is not this function, right? This is not equal to x minus 2 times 2x plus 1. Right? For starters, if I multiply this out, I'm going to get a cubic. This is going to be an x cubed here. I'll get another x cubed there. So if I were to multiply this out, I'd get 2x cubed at least. Well, there's no cubes in this. This is a quadratic. So I know right off the bat, these two functions are not equal, so this is not the antiderivative. There is no kind of product rule. And if we scroll up, the only rule we have is for addition and subtraction. That if I take the definite integral of this function plus or minus this function, then it splits up over addition. There is no rule, there is no product rule for integrals. There's similarly not a quotient rule. So this is the wrong way to go about this problem. So what's the correct way? So the correct way, so let's just put a big X through all of this because this is not the right way to do it. So the correct way, the antiderivative of x minus 2 times 2x plus 1 with respect to x Well, I'm going to have to do the algebra first. This is equal to 2x squared. Then I have an x and a minus 4, so that's a minus 3x. And then it'll be minus 2 dx. So these are equal. I've just done the algebra here, and now I could use my sum and difference rule and say, oh, well, this is equal to 2 times, a little room, 2 times x cubed, and then I have to divide by 3, minus 3 x squared, and now I have to divide by 2, minus 2x, plus a constant. That is correct. This is the correct answer and the correct method of computing that antiderivative or indefinite integral.